Hi everyone, we are from Group 2 and we will be discussing papers regarding AI game playing, the specific approaches in each of them, and evaluating their strengths and weaknesses. We chose to explore the game domain as games like Atari and Go have become ubiquitous in AI and have a wide range of complex AI applications. There are many types of games: fully and partially observable games, turn and non-turn based games, single and multi-agent games. Choosing games allows us to explore the various algorithms, policies, pruning techniques, and exploitation trade-offs in reinforcement learning. Our group chose to discuss 4 different games: chess, Go, 2048, and Dota 2. These are the papers that we'll be discussing. We will base our evaluation on the following: the strengths and weaknesses of the algorithms, importance of search in game algorithms. An observation of interest was that across all papers, implementing search algorithms tend to improve the results substantially. And finally, the importance of self-play in game algorithms. First, Deep Blue. Deep Blue is one of the most popular chess machines to be created, as it was the first computer system to defeat the world chess champion in 1997. This was a breakthrough success, and it proved to the world that AI supercomputers could compete with and even beat humans. So for the development of Deep Blue, the final version of Deep Blue is actually called Deep Blue 2, which is a product of multiple improvements to prior chess machines. First, there was Chip Test and Deep Thought, which could explore 500K and 700K positions. And then there was Deep Thought 2, which implemented multiprocessing, hardware evaluation, and search software. And then there was Deep Blue 1, which had 36 nodes, 216 chess chips, and could explore 50 to 100 million positions per second. And finally, Deep Blue 2, which had a newly specialized chess chip, improved hardware and software searches, and parallelized search. It could explore 330 million positions per second. For the Deep Blue chess chip, it was a specialized chip with a redesigned evaluation function. It had 8,000 handcrafted features and hardware, and it employed specialized move generation. It could generate all moves that attack opponents' pieces, all moves that evade checks, and all moves that take control of the center of the board, to name a few. The search speed was 330 million positions per second. The architecture had 3 layers: the master, which controls the top-level searches and communicates to the workers, which executes additional search and passes leaf positions to the chess chips. These chess chips did the final levels of the search in the tree. Deep Blue implemented parallel search in both software and hardware. For the software, it utilized a transposition table, which is a cache of all past moves and visited positions. It implemented a dual credit approach built on top of the alpha-beta search algorithm. The alpha-beta search prunes out the branches of a search tree to decrease the number of leaf nodes to explore. Next, for the hardware, the search that was done on the hardware was faster and relatively simpler compared to the software search. They utilized quiescent search, which identifies nodes that have unstable values and explores them further. This allows us to compute more accurate values and addresses the horizon effect. The horizon effect is the inability to detect potential opportunities or threats beyond a given depth. In this photo, you can see that the alpha-beta search stops searching at a certain horizon. However, if at this horizon there are unstable values, quiescent search will choose to explore these nodes further and get a more accurate evaluation to get a better value. Next, we will be discussing reinforcement learning for the game of Go.
Hi everyone, I will be talking about reinforcement learning for the game of Go. Patrick previously introduced Deep Blue, which was an achievement in 1997 for chess. Over the years, the algorithms improved, and more recently, DeepMind developed AlphaGo, AlphaGo 0, Alpha 0, and Mu 0, each of which achieved their own breakthroughs in the game of Go. Go is represented by a 19 by 19 board, and is a 2-player game where one player places the white stone and the other player places the black stone. It is a perfect information game and is fully observable, and the goal is to gain more territory than the opponent. DeepMind first started building AlphaGo in 2016, which uses neural networks and tree search to master Go. It uses playing data from the KGS Go server with the rules of the games as inputs. The second iteration is AlphaGo 0, which is developed in 2017. This time, the algorithm is not given any playing data. Instead, it learns to play completely on its own. The third iteration is Alpha 0. This time, with just one algorithm, it managed to achieve state-of-the-art results on 3 perfect information games, namely Go, chess, and shogi. And the most recent iteration is Mu 0, where the algorithm was not even given rules for each of the games. And in addition to the 3 games that AlphaZero mastered, mu0 also mastered Atari. Generally, DeepMind's algorithms uses convolutional neural networks. As Go is rotationally and reflectively symmetric, data augmentation and board position transformations can be performed during training for AlphaGo and AlphaGo 0. However, this cannot be applied to AlphaZero and mu0, as chess and shogi are asymmetric. Next, I will give a detailed breakdown of AlphaZero. This is a more generic version of AlphaGo 0 as it is applicable in chess and shogi as well as Go. Rules for the 3 games are given to the algorithm, but playing data are not provided. The algorithm takes the board position as input. The input is of shape 19 by 19 by 17, where there are 17 features, each of size 19 by 19, which represents the Go board. At each iteration in the training, MCTS selects moves for both players and saves the results in the search tree. At initialization, the parameters of the neural network are randomly initialized and are updated by minimizing the MSE between the predicted outcome and game outcome, and by maximizing the similarity of policy vector to the vector of search probabilities. The updated parameters are then used in subsequent iterations of self-play, and the rewards are -1 for loss, 0 for draw, and +1 for win. This is different from AlphaGo and AlphaGo 0, as those 2 algorithms does not take draws into account since Go does not have draws. AlphaZero uses MCTS, where the nodes represents the board positions and the edges represents the actions. For each position, MCTS calculates the policy and the value function. The search tree is expanded by simulating moves, and for each simulation, an action that has a low visit count, high move probability, and high value is selected. These are then averaged over the list states of simulations that selected the exact same action from the same state, and a probability distribution over the actions is then written. For the results, focusing on Go, the red line shows the performance for AlphaGo Li, the green line shows the performance for AlphaGo 0, and the blue line represents AlphaZero. We see that AlphaZero outperformed AlphaGo Li after training for about 8 hours at 165,000 steps, and maintains the performance from AlphaGo 0. The next algorithm is mu0, where a novel approach to model-based reinforcement learning is introduced. The algorithm achieves state-of-the-art in Atari 2600, while maintaining the performance for chess, shogi, and Go. This time, mu0 learns completely by itself. It was not given any playing data to learn from, nor was it given rules to the game. The idea of the algorithm is that it models the aspects of the environment that allows the algorithm to make decisions. mu0 predicts 3 key elements: the policy, the value function, and the immediate reward. It is represented by 3 functions: the representation function where it takes input observations and maps it to the hidden states, the dynamics function where it takes the hidden states from the representation function and takes previous hidden states of the dynamics functions as inputs, and then computes an immediate reward and a new hidden state via a recurrent process. The third function is the prediction function, where it uses the same architecture as AlphaZero and predicts policy and value based on the state. mu0 also employs MCTS. It uses it with UCB to select the actions, similar to AlphaZero. The difference from AlphaZero is that mu0 adds intermediate rewards and discount factor on the future rewards, and there are 3 objectives: to minimize the error between the predicted policy and the search policy, the error between the predicted value and the target value, and also between the predicted reward and the observed reward. The results for mu0 can be seen in the diagram, again focusing on Go. The orange horizontal line represents the AlphaZero's ELO score. Generally, mu0 performed better than AlphaZero despite using less computation per node in the search tree. Next, Kenneth will be introducing the game 2048.
Hi everyone, I'll be talking about the game 2048. The game 2048 is a fully observable, single-agent game played on a 4x4 grid. Each tile can be empty or contain a value in the power of 2. The actions are to slide left, right, up, and down to merge adjacent tiles with equal values. Legal moves available are actions where at least one tile is slid. Each time an action is taken, a random tile is generated with probability that value is 2 of 90% and probability that value is 4 at 10%. The objective is to achieve one tile with a value of 2048. The player can continue to achieve higher scores even after achieving 2048. Technically, it is possible to achieve the tile of 2 to the power of 17. The game can be modeled with an MDP solution but has too large of a state space to practically do so. So this is the first paper that we'll be talking about, deep reinforcement learning for 2048. In the paper, they first attempted two approaches of policy network. The epsilon greedy approach, where actions were taken with a random factor of epsilon, and a probabilistic approach where the actions were taken according to the output's probability distribution. The policy network has an input x, where x is an element of a binary value to the power of 256. The output layer is of size 4, representing the actions up, down, left, and right. The findings were, both approaches face a cold start problem. The probabilistic model has achieved 1024. We think that the model might have learned a valuable way to quickly merge multiple tiles to gain more rewards and might not have learned an advanced strategy for the game. With decreasing probability on some state actions for the probabilistic approach, it might not be able to explore any strategy in the long run. Subsequently, an attempt to fit several human played games on the network displayed overfitted predictions and were not scalable. In the next experiment, they made use of approximate dynamic programming and attempt to teach the policy network a human's perspective of the game and the game physics. The algorithm moved according to the basis function that governs the decision. This is formed out of 4 indicator functions: the largest tile in the corner, the descending tiles along the vertical, horizontal, and diagonal axis for the largest corner. Unfortunately, no quantitative outcomes were shared. It was mentioned that the results were not satisfactory. We see that the problem with this approach is that it might not be accurately representing the value of some state transitions. For example, when we take an action and move from state 0 to state 1, it is possible that a random tile would be appearing right above the largest corner. This result is less desirable, but it's not reflected in the heuristics and is considered as a descending vertical value. Also, human strategies become much more complex in the later part of the game with lesser available empty tiles. Last but not least, in this paper, Monte Carlo tree search was trialed. Similar to AlphaGo's approach, it tapped into the existing policy network. Actions were selected according to the upmax of action value function. The expansion stage was done where only 2 tiles were simulated. I guess their version of 2048 game only spawned 2 tiles. In the simulation, the value of the leaf node were updated according to the maximum attained tile over 2048. Finally, the visited states were updated according to the counts and the average value of the results. This approach gave a better space for exploration. However, expansion and simulation for the initial stages of the game are expensive due to a higher number of possible empty tiles. And more importantly, the human corner strategy is a long-winded approach. It will take extra steps to achieve the same highest valued tile. This human strategy is supposed to increase the chance of proceeding further in the game and in the long run obtain a higher score. Therefore, the limited depth set in this approach might not be sufficient to learn this strategy. Now, I will show you how MCTS is being played. We have talked about policy search approach, one of the approaches of scaling up. The next paper, Mastering 2048 with Delayed Temporal Coherence Learning, Multi-Stage Weight Promotion, Redundant Encoding and Carousel Shaping will focus on functional approximation. This paper is a continuation from their first paper, Temporal Difference Learning of N-tuple networks for the game 2048. Some basic concepts required for this paper are, this approach was to use temporal difference by trials without incorporating human experiences, something different from the policy network paper. The N-tuple network, the function approximator, was used to represent the state of the game. 500,000 games were played for 3 methods: the cleverly designed temporal difference after state method, the temporal difference state method, and Q learning. The after state method is a concept of breaking down the game into 2 steps. First, the deterministic state when applying an action, the after state, and second, when a random tile is generated. The later section of this paper improved the N-tuple network by exploiting the symmetrical factor of the game. The results also shows that successful model, especially for an after state approach. Back to our paper of focus. In this paper, we look into improving temporal differences after state approach and tuple network model by applying additional mechanisms to the learning process. The experiments played for the game within 10 to the power of 10 actions. Performance were measured for a one-step look ahead 1-ply method and a depth of 3 expecting match 3-ply method. The 4 categories of experiments are adaptive learning, delayed temporal differences, multi-stage promotion, carousel shaping, and redundant encoding. At learning rate alpha, a learning rate alpha is applied in a temporal difference algorithm. This is important to step out of the plateau. Although applying momentum approaches in the long run give no substantial differences in the results, having a good learning parameter accelerates the learning process, which is what we always want. The approaches of adapting learning were temporal coherence, where the learning rate changed according to a deviation of the sum of errors over the sum of absolute errors, and an auto-step approach where they normalize the step size with an upper bound limit on every update. Both methods requires more N-tuple networks, a larger memory, and a longer learning time. Temporal coherence displayed the best performance. The delayed temporal difference seeks to solve the bottleneck of the update horizon. Originally, each update involves a cumulative computational cost. This method stores H states and errors. Instead of updating them immediately, they were updated by a cumulative approach. Because the error values were small enough to be stored in the cache, a major reduction in learning speed for the temporal coherence approach was observed. Next, the multi-stage weight promotion, an attempt to improve the results by learning the game in different stages. In order to appropriately learn each stage without having to restart from ground zero, the weights of each stage were initialized from a corresponding preceding stage weights. This method was more effective in the 3-ply method. This model was slower in learning. Finally, the carousel shaping tries to compensate the lack of data in the later stages of the game. It carousels the data available in different stages where there are no more episodes or stages to learn. It restarts to stage 0 again. This is one way to solve catastrophic forgetting. Redundant encoding adds redundant data features into the network. Although it contradicts the principle of function approximation, they can improve learning by quicker generalization. The results show significant improvement in the 3-pi network. The additional 4 tuple and 3 tuples were crucial to the improvements. And this process, however, decreases the learning speed as more parameters were involved. The time taken was observed to be twice longer. In conclusion, we learned how we can improve temporal differences, how decent approximation can significantly improve reinforcement learning, and tuple networks are good approximators for board games. The importance of a good search algorithm, a depth of 3 expecting max method can have a better result compared to a 1-ply method and show greater improvement when applied with learning mechanisms. Between the functional approximation and policy search approach, in our opinion, the after-state design was clever and made the difference. Having said that, the approaches do not scale well with larger state space and dimensions and require large memory due to large parameters required in training. Policy search is difficult to apply in the case of an unknown validity of the policy and insufficient human played data. What could be incorporated in a deployable successful model, given the lack of human input data and confident basis function, is to first work on value state approximation and then use the data generated to work on policy search to be deployed for production. Next, I will be passing on to Patrick for Dota 2.
For our last paper, I'll be discussing OpenAI 5 for Dota 2. Dota 2 is a real-time strategy game with 5 players on each team. OpenAI 5 was the first AI system to defeat an esports world champion team. Dota 2 was a new challenge for AI because the state action spaces were continuous and more complex. Players also only had partial information on the current game state. There were far more complex decision trees as compared to turn-based games such as chess and Go. For the Dota 2 problem model, first we know that Dota 2 has long time horizons. For an average game, which takes around 45 minutes at 30 frames per second, there will be 80,000 picks per game. OpenAI 5, which observes every 4 frames, will generate 20,000 moves, which is extremely large compared to chess, which usually ends in less than 40 moves, and Go, which usually ends in less than 150 moves. Dota also has a partially observed state. The only thing it can see are the 5 screens, 1 for each agent. The agent can only see the area around them because the rest of the map is covered in a fog, as opposed to chess and Go, which are fully observable. Lastly, Dota is high-dimensional and has a continuous action space. There are 170,000 actions per hero, and at each tick, there are around 1,000 valid actions, as opposed to chess, which has 35, and Go, which has 250. For the OpenAI 5 architecture, there were 5 identical networks. 5 single-layer 4096 LSTMs. Each of these receives the partially observed game state and the hero embeddings and outputs the value function, which predicts the reward, and the output actions using their action heads. These actions are parameterized with 4 parameters: the number of ticks to delay the action, the x and y coordinate, and the action which it has to select. OpenAI 5 also used handcrafted rewards based on human metrics. There were different techniques that they used for these rewards. First, they have to be zero-sum, because in Dota, only one team can win. The average rewards of the enemy are subtracted from a player's reward. Second is game time weighting. Agents in the game become exponentially more powerful as the game progresses. This means that at certain points, they have to decay the rewards of each agent, because if not, the rewards will start to explode. Lastly, team spirit. Team spirit is a weighting factor that they implemented to determine whether a reward is given to an individual or distributed to a team. Because sometimes there are occasions wherein a player has to sacrifice his teammate, which is considered an individual reward, but overall it's for the good of the whole team. Next, OpenAI 5 used proximal policy optimization to train their policy. It's easier to tune and relatively simpler to implement while maintaining the same performance. The objective is to minimize the cost function while also maintaining a minimal difference between the old and the new policy. Basically, this is the expectation of the advantage times the minimum between the reward or the clip version of the reward. The reason they do this is because they want to minimize the difference between the old and the new policy while at the same time maximizing the advantage. Finally, OpenAI 5 utilized self-play. Their model was trained by playing against itself without any human gameplay data. With every batch of games, the model gradient policy is updated. The current model played 80% of its games against itself and 20% against its past versions. This helped it learn an accurate distribution of opponents of various skills and strategies. As opposed to taking the average policy, the latest set of policy parameters was taken. It was also trained continuously over the course of 10 months to improve and eventually beat the world champions. Next, we will go into our evaluation. So for the search algorithms used by Deep Blue in chess, first we have alpha-beta search. Alpha-beta search simplifies the tree by pruning out branches that need to be explored. This is critical in increasing the efficiency in exploring chess positions. Chess can be played using 4-ply search with more than 36 branches per node, resulting in 1 million leaf nodes. Using an optimal alpha-beta pruning technique, you can prune 99.8% of these nodes and reduce the required search to around 2,000 nodes only from 1 million. Next is quiescent search. Quiescent search identifies positions which are unstable and chooses to evaluate them at a deeper level to get a more accurate value. This is effective in addressing the horizon effect, which prevents us from detecting potential opportunities or threats beyond the given depth. The combination of alpha-beta search and quiescent search creates a balance between search efficiency and accuracy. These searching methods complement each other and were critical for the success of Deep Blue.
Next, I will be talking about the importance of search in Go. MCTS is used in all 4 Go algorithms. AlphaGo uses MCTS to combine the policy and value networks to perform look-ahead search to select actions. In AlphaGo 0 and Alpha 0, neural network guides the simulations in MCTS to select the actions. For mu0, MCTS is used to select actions similar to Alpha 0, but intermediate rewards and discount factor on future rewards are included. Although without MCTS, AlphaGo's policy and neural networks already exceeded the performance of other Go algorithms. The algorithm that actually has the best result is the one with both policy and value networks with MCTS to perform the look-ahead search. Also, AlphaGo 0 and the subsequent iterations continually improves on or maintains the performance from the previous iteration. And this highlights how MCTS can actually improve the neural network policies to determine the best actions to take in the domain of games. For 2048, although MCTS did not display these satisfactory results, this is most likely due to poor heuristics applied to the search tree. The tree depth expecting max method can have a better result compared to the 1-ply method and can show greater improvements when applied with the learning mechanisms. Next, I will be evaluating the importance of self-play in game algorithms. DeepMind used self-play in all 4 Go algorithms. In AlphaGo, the reinforcement learning policy network won 80% of the games against the supervised learning policy network. In the other 3 algorithms, as human playing data was not provided, the algorithms learned to play the game completely on their own through self-play, each of which managed to beat its own predecessor. And this shows how powerful self-play can be in the game domain.
Next, I will be discussing OpenAI 5 Dota 2 self-play. Dota 2 has a complex and continuous state action space, so the search method used in chess, Go, and 2048 won't necessarily work. Self-play has proven to be an effective method in tackling games with complex and continuous environments, as it allows for the agent to learn without supervision. They were able to simulate randomized stochastic environments between 2 teams, which is crucial for the agents to learn the intricacies of the game. Having an efficient self-play system allowed OpenAI to simulate 180 years worth of games every day with the computational resources that they had. However, one of the drawbacks of self-play is that at the early stages of training, the agents appear to be dumb and cannot necessarily identify the objective or what they're supposed to do. This can be addressed by randomized domain initializations of the environment. To conclude, in this project, we explored in detail the application of artificial intelligence in games, in particular in chess and Go, 2048, and Dota 2. We evaluated the algorithms used in those games and analyzed the effectiveness of search algorithms on turn-based games. We also discussed the advantages of self-play and how it enables the agents to learn in both simple and complex environments. These are the references we used for our presentation. Thanks for watching to the end of the video.